We started section 4.3 last time, and we were learning here how we can use derivatives to help us figure out the shape of a graph of a function. And so far we've looked at how the first derivative helps us determine where the graph is increasing and decreasing. The next thing we're going to do in this section, starting today, is to see how the second derivative can tell us where the graph has concave up or a concave down curve. And then at the end of the section, we'll put everything together and practice doing curve sketching. In other words, if you're given a formula for a function, use all these techniques we've been learning to help determine what the graph of that function looks like. First, let's just do a quick review of the concept of concavity that we introduced last time. So you can see the two blue curves here. They're both increasing, but the shape of the curve is very different. So the curve on the left, we refer to this as concave up, and the curve on the right, concave down. So one way to think about these, concave up looks like part of a bowl that's upright, and concave down looks like part of a bowl that is upside down. The official definitions have to do with tangent lines, right? So here we see the tangent line. On this case, the curve always lies above the tangent lines. That's concave up. And its opposite over here, the curve always lies below its tangent lines. So this is a concave down curve. Now we're going to discuss how to relate this to the second derivative. So notice on the graph on the left, as we move from left to right, and we look at the various tangent lines, notice that the slope is increasing as we move along. The slope is f prime, right? So as we move left to right, the slope, which is equal to f prime, increases. So now we know that f prime is an increasing function. Now let's apply what we learned about the first derivative. If a function is increasing, the derivative of that function is positive. So that tells us if f prime is increasing, the derivative of f prime is positive. Okay, so the derivative of f prime is what we call f double prime, and it would be positive. Now let's make the same observation, or a similar observation, for the concave down situation. Again, as you move to left to right, notice the slopes. They become less steep, right? They get closer to zero, which means they're decreasing. Okay, so again, as we move left to right, the slopes, which are equal to f prime, decrease. So now we've established f prime is a decreasing function. So we know that any function that's decreasing, its derivative would be negative. So we know the derivative of f prime, which is f double prime, must be negative. So notice we're making a connection between concave up with having a second derivative being positive, and concave down is associated with the second derivative being negative. Here we'll summarize the observation we just made as in what's called the concavity test. So we said that if the second derivative is positive on some interval I, that means the graph of f is concave up on that same interval. On the other hand, if the second derivative is negative over some interval, that tells us the graph of f is concave down on the same interval. So this is what I've been suggesting as we build up to this, that the second derivative tells us about concavity, just like the first derivative tells us where a function is increasing and decreasing. We looked at this graph last time, and we discussed how a single function can change its concavity. So in some parts of its graph it might be concave up and other parts concave down. So we went through this particular example of a graph of a function, and we noted that it started concave down, and then somewhere in here it switched, because over here, notice, you can tell it's concave up, and then at some point it switched again, right? So it switches several times. What I want to introduce here is the term inflection point. So if you have a curve y equals f of x, a point P on that curve is called an inflection point if f is continuous at that point and the curve changes its concavity, either from up to down or down to up. So let's identify some of the inflection points on this graph. So note, we already observed it starts as concave down, and then somewhere it switches to concave up. So you want to get so you can see where that happens. Now here we're kind of helped because it's labeled as a B, but we'll practice some of these where it's not pre-labeled for you later. But you can see that looks about right. Right to the left of that blue dot, it's still the upside down bowl, and to the right of the blue dot, it's now switched to a right side up bowl. So the point B is an inflection point. Let's keep going. So we're concave up, and then somewhere in here you can tell it's switched because this part's concave down. And so the point marked C is where it seems to switch. So that's another inflection point. So notice point D is another because it's concave down over here. And then at point D there's this sort of corner cusp type thing, and it immediately switches to concave up. Now remember, it said that f must be continuous at the point in order for it to be an inflection point. This is continuous at D. It has a corner, which means it's not differentiable, but it is continuous there. So that's another inflection point. Now notice here, this one, it's concave up to the left of that point, and it's still concave up to the right. So that's not an inflection point. At point P is, though, right? Because it's concave up over here, and then at point P it switches to concave down. So P is another inflection point. Let's look at this example. So we're given a figure that shows a graph of the population for honeybees. So notice here, the vertical axis is the population size, number of bees in thousands, and then on the horizontal axis, time measured in weeks. So the population starts very small, and notice it's increasing all the time. So the population is always increasing. But just saying it's increasing doesn't describe the whole situation, right? The curve is different in different places. So that has to do with the concavity, and the concavity is related to how the slope is changing at different points. The slope of the tangents is different. So let's discuss some of these questions. How does the rate of population growth change over time? When is this rate the highest? And then discuss the intervals where it's concave up and concave down. So starting at time 0, it's increasing but very slowly, right? It's not going up much at all for the first 5 or 6 weeks. Okay, so we'll say this first part is very slow growth. And here the growth is referring to the rate of population growth, right, that they asked us about. And then the rate picks up, so between this point and somewhere around here, notice the tangents are getting steeper all the time. So it's faster growth. And then right around, so look, before I say do any more, see if you can identify the inflection point on your own before I put it on there. Right, it takes a little practice to start being able to see these, but I would say probably around here. Right, to the left of that red dot, it's concave up. To the right, it's concave down. And notice it's right at that inflection point that the rate of growth, the tangent lines, right, start to flatten out. So the slopes start getting smaller when we pass this inflection point. So now the growth rate is slowing down. And the farther you go to the right, the more flat the tangents get. So the growth rate gets slower and slower the farther we go to the right, till it's almost, if it kept going out on, the slope would get close to 0. Okay, so the inflection point is our change of concavity, and that's relating to how large the rate of growth is. Notice to the left, our growth rates are getting really hot, really big, very steep. And as soon as we cross that inflection point, that it reverses and the slopes start getting closer to 0. They're decreasing. Okay, so the rate is the highest right before or right when we hit the inflection point. Okay, so this is just gives you an idea why we're interested in concavity and inflection points in a function that's modeling something real. So we just saw that the second derivative tells us about concavity. We can use that to derive this other test called the second derivative test. And the point of this test is it's just an alternate test for finding local max and min. So this is not a test for finding concavity, even though we're using the second derivative. So alternate test for finding local extrema. So let's read what the test says. So we have a function f, and we assume the second derivative is continuous near some x value c. So there's two cases, and both of them have f prime of c equals 0. Now what does that tell us? F prime of c equals 0 means that the tangent at x coordinate c has slope 0. In other words, it's a horizontal line. So the tangent at x value c on the curve is horizontal. So that's true in both cases A and B. Now let's look at case A. The second derivative at c is positive. So we know that means the curve f is concave up. I'm going to abbreviate that CCU at x value c. So let's sketch something so we can see what's happening here. I want to sketch a curve that is concave up, and when it passes through C, it has a horizontal tangent. So notice the horizontal tangent at C. Now notice that forces a local minimum at C. And that's exactly what part A says. If f prime of C is 0, meaning the tangent's horizontal, and the second derivative of C is positive, which makes it concave up, then the graph of f must have a local minimum at C. Let's look at part B. So in this case, f double prime at C is negative. So we know that the second derivative being negative tells us the function itself is concave down at that x-coordinate. So the picture that would go with this one, let's say C is here. I want to sketch a curve that's concave down, and when it gets to x-coordinate C, it has to have a horizontal tangent. That forces the curve to have a local max at x-coordinate C. And that's what part B says. So like I said, this test, the name can be confusing because when you see the second derivative test, you might think, oh, second derivative tells you concavity, so this is the test for concavity. That's not what it's for. Right? This is just an alternate test. Earlier we learned a method for finding local max and min based on where the function's increasing and decreasing, and we use the first derivative for all of that. This is an alternate to that test that lets you find local max and min based on these criteria here. Let's use the second derivative test in this example to find the local extrema of the given function. So we know for this test we're going to need both f prime and f double prime. So let's start with f prime. So it's a simple derivative for this function. So using the power rule on the first term, when we bring the 3 down in front, it cancels with the 1/3, and we reduce the power from 3 down to 2, so it becomes x squared. Second term, the derivative is minus 2x, and then minus 3 plus 0. Now remember, what we're looking for in this test are points C where f prime of C equals 0. So we're going to now set f prime equal to 0 and then solve for x. This is exactly part of the process of finding critical numbers. So we are finding critical numbers here, it's just we're only finding the ones that come from the case where the derivative is 0. So I set my f prime equal to 0, and then we want to solve this for x. So I'm going to try factoring. Looks like x minus 3 times x plus 1 will work. And then we set each of those equal to 0, solve each one, and we get positive 3 and negative 1. So these are potential, right? These are critical numbers. It's not all there could be more critical numbers, but it's the ones that make f prime equal to 0. So let's take them one at a time and plug them into f double prime. Now we need to first find our formula for f double prime. So we look at our formula for f prime right above where I'm writing and take the derivative of that, and we get 2x minus 2. Now let's start with x equals 3. I'm going to plug 3 into f double prime. And we get 6 minus 2, which is 4, a positive number. So remember, positive second derivative means concave up. And so if you just visualize that curve, a concave up curve, you can see we've got a local min at the x value we just tested, which was x value 3. Now let's take our other x value we found that made the f prime equal to 0, and that was negative 1. We plug that into f double prime, right? So that's both of those are getting plugged in here, right? So 2 times -1 is -2, and then -2, we get -4, clearly a negative number. That means concave down, so if you just visualize a concave down curve, we know it has to be a local max. So we've got a local max at the x value we just tested, which is -1. Okay, so we answered the question here. We found these two local extrema. We should have found the exact same answer if we had solved this problem the way we did earlier, using the first derivative to determine where the function's increasing and decreasing. So like I said, this test is just an alternate method to find local extrema. We want to apply several of the techniques we've been talking about to the curve with the equation given here. So we want to discuss the concavity, points of inflection, and then also the local max and min. So first of all, let's give this curve a function name. Just replace y with function notation f of x. And we know we're going to need first and second derivatives to discuss concavity. So let's go ahead and find those. And these are pretty straightforward derivatives. We get 4x cubed minus 12x squared for the first derivative. Now, the second derivative, look at the formula for f prime and take the derivative of that. So when you bring the 3 down and multiply it by the 4, we get 12x squared. And then for the next term, minus 24x. Now for each of these, I'm also going to factor them because that might be helpful later on. So going back to f prime, I can pull out 4x squared from each term. So in the first term, that leaves just x, and in the second term, it leaves minus 3. Okay, and then for f double prime, we can pull out 12x from each term. The first term, that leaves x, and in the second term, it leaves minus 2. Okay, so now we could answer any of these questions in any order, but I think I'll start with the second derivative test. Remember, that is to find the local max and min. So for this, we start with the critical numbers, but it's not all of the critical numbers. It's only the ones that come from setting the first derivative equal to 0. We don't include the ones that make the first derivative undefined. So critical numbers, we take our formula for f prime and we set it to 0. Now we wrote f prime in two ways, right? This first way, and then we factored it. It's going to be easier to use the factored form since it's equal to 0. So I'm going to take that formula, factored form, set it equal to 0. Now we've got a product equal to 0, so that means you set each individual factor to 0, and then you solve each one individually. So from the top one, we'll get x equals 0, and from the bottom one, we'll get x equals 3. So these are our two critical numbers that we're going to use in the second derivative test. So if you remember how this test works, we need the formula for f double prime, but we've already found that. And we're going to plug these numbers in. So let's first plug in 0 into f double prime. Okay, so just to point out where we're plugging in. And for this, you could use either version, the original or the factored. Well, if we use this one, when we plug 0 in, we get 0 minus 0, which is 0. Now what does that tell us? Remember, the second derivative test says if you take one of these numbers that you already know makes the first derivative equal to 0. Then you look at its output when you plug it into the second derivative. And if you get a positive number, that tells you one thing. If you get a negative number, it tells you another thing. But it doesn't tell you anything if you get 0. So this is actually, for x equals 0, the second derivative test is inconclusive. So we're going to need to use another method to determine if we have a local max or min at x equals 0. Let's go to our second number we found. Our second critical number was 3. So when we plug this in, it might be faster to use the factored form. 12 times 3 is 36, and then that's multiplied by 3 minus 2, which is 1. So the output is 36. All we care about, though, is that that's a positive number. So we have the f prime of 3 is 0, which is required to even use this test. And then the second derivative at 3 is positive. Remember, positive means it's concave up. And so if you visualize that, it means we're dealing with a local min. So we have a local min at x value 3. So we'll continue this example on the next slide, and hopefully we'll be able to determine what's happening at x equals 0. So let's see if we can figure out what's happening at x equals 0, right? This was one of our critical numbers, and we don't know. The second derivative test didn't work to tell us if we have a local max or min, or neither, right? It's possible a critical number is neither. Okay, so the second derivative test didn't work. But remember, we have another test for this. Let's try using the first derivative test. Now this test really just tells us where the function's increasing and decreasing, but then we use that result to find where we have local max and min. So for this method, we made a number line, and we put our critical numbers on the number line. So here we had 0 and 3 were our two critical numbers. Now technically there could be more. These are only the ones that made f prime equal to 0. The others come from where f prime doesn't exist, but notice f prime is a polynomial, so it exists everywhere. So there actually aren't any more critical numbers. And then we choose our test points. So I'll choose -1, +1, and 4. And then we plug these in to f prime, right? Make sure you plug them into the correct thing. Now the formula for f prime is right here, and the factored form is going to be easiest. So let's plug in our test point -1. The first factor will be 4 times -1 squared, and because it's squared, it's always going to be positive. The second factor, -1 minus 3, is negative. So that product will be negative. Our next test point is 1. The first factor, 4 times 1 squared, is positive. The second factor, 1 minus 3, is -2, so that's negative. Okay, so we've got another minus sign. And then when I plug in 4, 4 times 4 squared is positive. And then the second factor, 4 minus 3, is 1. That's positive. So the product of two positives gives us a positive. So then this tells us where the function is f is increasing and decreasing. So when we have f prime negative, that means f is decreasing. So over these two intervals it's decreasing, and then over here increasing. So notice at 0, when we get to 0, it's decreasing as we get closer to 0, and then it stays decreasing. So that kind of shape means there's no local max or local min at 0. That was the unknown one. If you look at 3, it changes from decreasing to increasing when we get to x coordinate 3. That means we have a local min there, but we already knew that. That agrees with what we found from the second derivative test on the previous slide. So we've now concluded that at x equals 0, there's no local max or min at x equals 0. And then just to mention it again, we've got a local min at x equals 3. So we've answered the part of the question about local max and min. We still need to answer the question about concavity and inflection points. So we've done partial problems like this. Let's go through the full method for how to determine this. This method is almost identical to what we just did here, where we used f prime and test points to determine where f prime is positive and negative. It's going to be exactly the same process but applied to f double prime. Okay, so let's start working on concavity. Remember, we're looking for where f double prime is positive or negative. That tells us about concavity. So what we do first is find where f double prime equals 0, because 0 is the dividing point between being positive and negative. So we start by setting f double prime equal to 0, and then solve for x. So look at the formula for f double prime just above where I'm writing, and I'm going to use the factored version. We set that equal to 0. Because we have a product equal to 0, that means we set each individual factor equal to 0 and solve each one individually. Okay, so from the top equation we're going to get x equals 0, and from the bottom equation x equals 2. Now notice what we just did was almost identical to how we find critical numbers, except for critical numbers we set f prime equal to 0. This time we're setting f double prime equal to 0, and then in either case you solve for x. So these are kind of like the critical numbers, except they're for f double prime instead of f prime. Then we're going to take these numbers that we just found, put them on a number line, choose test points, and then instead of plugging into f prime, we're going to plug them into f double prime and do this exact same process to determine where f double prime is positive and negative. Okay, so we'll continue that part on the next slide. So again, we're going to make a number line and put 0 and 2 on the number line. We had just found the two values that make f double prime equal to 0, and those were the numbers 0 and 2. So now we're going to make a number line and put those numbers on the number line in order from smallest to biggest. And then that created some subintervals, so we're going to choose test points in each subinterval. How about -1, +1, and 3? Then we're going to plug these in to f double prime. So the formula we're going to use for f double prime is right here. The factored form is going to make this easier. So when we plug in -1, the first factor, 12 times -1, will be negative. The second factor, -1 minus 2, is negative. So that product is positive. Next test point is 1. The first factor is 12 times 1, that's positive. Second factor, 1 minus 2, is negative. So that product is negative. And then our last test point is 3. 12 times 3 is positive. 3 minus 2 is positive, so the product here would be positive. So you can see this is really the same process we did in the first derivative test when we were finding where it's increasing and decreasing, right? In that case, a plus here would tell you increasing and a minus would tell you decreasing. But this time we plugged into f double prime, so it's going to tell us about concavity, not increasing and decreasing. So we learned earlier that if the second derivative is positive, that means the curve is concave up, so CCU. When the second derivative is negative, concave down, and then here it's positive again, concave up. So now we can summarize about the concavity. So we'll say the original curve f is concave up on the x interval. So notice our concave up here. This interval goes negative infinity on the left up to 0 on the right. So using interval notation, that's what that interval would look like. But then there's another interval where it's concave up. On the right, everything to the right of 2. So this interval goes from 2 on the left to infinity on the right. And then we can say f is concave down on the interval from, in the middle there, between 0 and 2. Okay, so that answers the question about concavity. Now let's look at inflection points. So remember, an inflection point is where an x value where it changes concavity. If you look at our number line, notice at x equals 0 it changes from up to down. That means x equals 0 is an inflection point. And then our other point here, 2, x equals 2, notice it changes on either side. Concave down to the left of 2 switches to concave up on the right. So x equals 2 is also an inflection point. Now sometimes we like to express our inflection points as ordered pairs. So if you want to find the y value that goes with it, you have to plug in that x value. So for x equals 0, we plug 0 back into f, and we get 0 minus 0, which is 0. So the y-coordinate is 0. So as an ordered pair, we found x is 0, y is 0 is an inflection point. Then we'll do the same thing when x equals 2, the corresponding y value would be f of 2. So notice when you plug 2 in here, you'll get 2 to the 4th minus 4 times 2 cubed. That comes out to negative 16. So our ordered pair here is 2 for x, negative 16 for y. So those are our inflection points as ordered pairs. Okay, so we've answered all the questions. If you had a graphing calculator and you wanted to sketch this just to see how this matches up with what we found, I'll try to sketch it by hand, but this is basically what it would look like. So it starts out coming down, it hits, kind of flattens out as it hits the origin, then it becomes negative slope again, coming down, turns around and goes up. Okay, and the points where these changes happen, let's see, this is 3, about right here. Okay, so what we found earlier was that it was decreasing to the left of 3, and then after 3, if we got to the right of 3, it becomes increasing. So you can see that matches here. We also found a local min at 3, you can see that. And 0 was a critical point, and you can see it has a horizontal tangent, which is why it was a critical number. But notice it's not a local max or min, and that's what we found earlier. We actually found it was decreasing on either side of 0, so no local extremum there. And then for concavity, so we found to the left of 0, it's concave up. We can see that here. Between 0 and 2, concave down. You can also see that here. And here's 2 right here. Let me label that. Our inflection point was about here, right? That's the point 2, -16. And then we had another one at 0, 0. Those are the points where the concavity changes, right? So we can see concave up, and then when we pass this point, it becomes concave down. Past that inflection point, it becomes concave up, and that matches the intervals that we saw here. So this example is getting us really close to being able to sketch a curve, right? I gave you this curve, right? A computer or calculator could be used to generate that, and then we just saw how everything we found corresponded. The next step of this process, which we'll get into later in this section, is take all the calculations we did for a problem like this in terms of increasing, decreasing, local max, local min, and concavity, inflection points, and put all that together to be able to create this graph yourself without needing a computer to do it for you. In this example, we're going to put together all the techniques we've been learning to create a graph of this function. So notice the formula for f. This is something that might be a little difficult to graph using the methods from pre-calculus, right? It's not an obvious transformation of a familiar function, and the formula is just a little too complicated to know right away what that graph would look like. So this is where calculus comes in. We can use the first and second derivatives to help us figure out what this graph would look like. So the things we want to look for are, where is this graph increasing and decreasing? Where are the local extrema? And then determine the concavity. Where is it concave up and down? So let's start with increasing, decreasing. So that's where we use the first derivative. So this test we learned at the beginning of the section is where we found the critical numbers and put them on a number line. That was the basic method we're going to use here. So to find the critical numbers, we need f prime. Let's go ahead and calculate that. So we get 3x squared minus 3 plus 0. And then you could factor it, right? That usually is helpful. So here, if we factor out 3, that leaves x squared minus 1. And then that factors further, 3 times x minus 1 times x plus 1. Okay, now let's find our critical numbers. So there's 2 things you have to check for critical numbers. One are values that make f prime equal to 0. The other are values that make f prime undefined. So starting with f prime equal to 0, just take our factored version of f prime and set it equal to 0. Since it's already factored, we just take each individual factor and set it to 0. Notice I don't need to set 3 equal to 0 because there's no x in that, and 3 never equals 0. And then solving each one of these, I get x equals positive 1 and x equals negative 1. So these are 2 of my critical numbers. Now let's look at the second condition, any values that make f prime undefined. But notice f prime is a polynomial. Those are defined for all x. So we're not going to get anything from that condition. So we just have the 2 critical numbers. So let's put them on a number line in order from smallest to biggest. That creates our subintervals, and then we choose test points in each subinterval. So I'm going to choose -2, 0, and +2. Now we plug these into f prime. So I put up here the reminder that I'm plugging into f prime. You have to think carefully because in all these methods we're learning, sometimes you plug into f, sometimes plug into f prime, and sometimes into f double prime. So always be careful that you're plugging in the right place. So for increasing, decreasing, we plug into f prime. Now it might also help if you write the formula here so you can clearly see where you're plugging in. So I'm going to write the factored version of f prime. Okay, so let's plug in -2. So the first factor, 3, right, that's positive. The second factor, -2 minus 1, will be negative. And the third factor, -2 plus 1, is negative. So that product will be a positive number. Okay, next test point is 0. So the first factor, 3, that's always positive. The next factor, 0 minus 1, is negative. And then 0 plus 1 is positive. So the product of those three will be a negative number. And then our last test point is 2. So the first factor, 3, is positive. 2 minus 1 is positive. 2 plus 1 is positive. So that product, positive. Now this is the f prime values, being the signs being plus or minus. That tells us increasing and decreasing. So a plus means increasing. Minus means decreasing. And then here it's plus again, so increasing. So let's summarize the results. F is increasing on, we just found one interval, and that went from 1 to infinity. And then we found F is decreasing. It was actually 2 intervals. Oh, sorry, I was wrong. Increasing on 2 intervals. So there's also this interval to the left of -1, so let's back up here. Negative infinity up to -1, it's also increasing. And then it was decreasing just on the one interval between -1 on the left to +1 on the right. Just a reminder, when you're writing these intervals, make sure you do not use test points as your endpoints. I should not be using -2, 0, or 2 as any endpoints on these intervals. The endpoints have to come from the critical numbers that were originally marked on the number line. Okay, so that takes care of number 1, finding where it's increasing and decreasing. So let's move to local extrema. Remember, you have 2 options for this. You can either use the results of increasing, decreasing, or you could use the second derivative test. But since we've already done the work to find increasing and decreasing, it's going to be fastest just to use that. There's no need to, I think it would be more work to do the second derivative test here. So let's look at our results here. At -1, right, as we come into it, it's increasing, and then it switches to decreasing. So if you can kind of visualize what's happening there, that means we've got a local max. And then at our next critical number 1, it comes into it decreasing, and then when it passes 1, it switches to increasing. That image tells us we have a min there. Okay, so let's answer the second part about local extrema. We determined we have a local max at x equal -1, and we have a local min at x equal 1. Now it's going to be helpful to find the ordered pairs for these points. Right now we just have the x coordinate. We're out of space here, but on our next slide we'll finish this by finding the y coordinate that goes with each one, because these are important points on the graph and we want to plot them exactly where they are. So we need the entire ordered pair. So that's where we'll start on the next slide. On the last slide, we were considering this function. We already calculated f prime, put it in factored form, and we did all the work to determine we have a local max at x equal -1 and a local min at +1. So what we were going to do next is find the y coordinate that's paired with each one. So this is just like when you're plotting points. You plug back into the original f. So we're not plugging into f prime or f double prime here, just f. So f of -1 will be -1 cubed, which is -1, minus 3 times -1 is +3, and then followed by +3 again. So that comes to 5. So our local max as an ordered pair has x coordinate -1, y coordinate 5. Now for our local min, we know x is 1, so now we're going to plug in 1 into f to get the corresponding y value. So looking up here at the formula for f, plugging in 1, right? So 1 cubed is 1, minus 3 times 1, plus 3, that simplifies to 1. So our local min, as an ordered pair, the x-coordinate was +1, and the y-coordinate was also +1. So the third step that we decided, we're going to look at concavity. Okay, so for concavity, of course, we're going to use the second derivative. So let's calculate f double prime. Now we have our formula for f prime up here. It's going to be easier to use the version that's not factored for taking the derivative, right? If we used the factored form and tried to take the derivative, we'd have to use the product rule. It's a lot less work to use the unfactored version, right? So derivative here, using the power rule, we get 6x minus 0, so it's just 6x. Okay, so the next thing, we did this process in our last example, we're going to go through the same method we just did with f prime to determine increasing and decreasing, but we're going to use f double prime. So the analog of critical numbers is find the values where the second derivative is 0. So we're going to set the second derivative to 0. So that means we have 6x equals 0. Solve that for x, we just get one value, x equals 0. So that's the analog to the critical numbers, so those are the numbers we put on our number line. So in this case, there's only one number to put on the number line, and that's 0. So in terms of our test points, right, there's only 2 subintervals to choose a test point in. So I'm going to use -1 and +1. Now here's the slight difference, right? Instead of plugging into f prime, we're going to plug into f double prime. And write the formula here might be helpful. When we plug in -1, we get 6 times -1, which is negative. When we plug in +1, we get 6 times 1, which is positive. And then we know that minus means concave down, plus means concave up. So now we can discuss here what our concavity is. So actually, let me use the abbreviation. So concave up on the interval that's to the right of 0, so 0 to infinity. And then f is concave down to the left of 0, so that goes from -infinity up to 0. And then one other thing that's helpful when you discuss concavity are the inflection points. Okay, so inflection points are the numbers where they come from these points that you've marked on your number line, possibly. But any point here where it changes from up to down or down to up, and you can see at x equals 0, it does change. Okay, so when you set f double prime equal to 0 and solve, it's tempting to call all these solution inflection points, but they're not necessarily inflection points, because when you completed your number line, let's say it was concave down on both sides, that would make this not an inflection point. But in this case, it turned out this number was an inflection point. Now, just like max and min, it can be helpful to write your inflection point as an ordered pair so we know exactly where it is when we graph it. So to find the y value, you always plug back into f. So when x is 0, right, look at the formula for f up here. 0 minus 0 plus 3. So we get the y value is 3. And so as an ordered pair, our inflection point has x coordinate 0, y coordinate 3. So now we've found all the pieces, we're going to try to fit them all together on our next slide to create the graph of this function f. So we've copied all of our results that we've gotten so far for this function, and now we're going to start putting all that onto our graph. So I make my xy axes, and when I choose the tick marks, I need to look at my points to help decide what scale to use. So looking at all the numbers I've written there, the important x values look like they're 1, -1, and 0. So I don't need to go very far. I do want to go a little beyond all the points I see there. So maybe we'll go out to 3 in each direction on the x-axis. And then for the y values, notice these are x intervals, they don't contain any y values. But here, these are ordered pairs, so I need to go up at least to 5 and probably a little beyond that. And here's a 3 and a 1. So maybe we'll go up to 6 on the y-axis. And we'll go down, we don't need to go down quite as far, but about that far. Okay, now let's plot points first. So like I said, these are x intervals, these are x intervals, those aren't points. But we have a local max and a local min that we want to plot. So -1, 5, that's a local max. And if it helps, you can make a note so when we sketch it, we'll make sure we make that point a max. And then the point 1, 1 is a local min. And then we have an inflection point at 0, 3. I'll just put IP for inflection point. Okay, those are the only points we've plotted so far. If we decide we need more, we can make a table and plot some extra points. But let's see how we do with just this. Now, let's look at our intervals. So increasing, decreasing, we had this number line. I'm going to recreate it down below the graph. And if you look at our intervals up here, the only numbers we see here other than infinities are 1 and -1. So I'm going to mark off, line them up. Right here's -1. Here's +1. So notice in the box with our results, we said it's increasing on to the right of 1 and to the left of -1. And then in between is where it's decreasing. So when we sketch the graph, we want it to start out increasing, get to this max, switch to decreasing, pass through these two red dots. When we get to this red dot, that's where it switches back to increasing. So we're already starting to get a feel for the shape. But before we start drawing, let's make sure we think about the concavity. So concave up to the right of 0, concave down to the left of 0. I'm going to put in another number line down here. And 0 was the dividing point. So to the left of 0 is where it was concave up. To the right of 0, concave down. Okay, now let's start drawing. Now before I want to get a feel for the shape before I actually put anything down. So we already knew it was increasing on the left part here until it gets here. But when we make that curve, it needs to be, sorry, I got those reversed. It should be concave down to the left of 0. Right, if you look at the intervals, that's what it says, and it should be concave up to the right of 0. Okay, let's try this again. So I know I'm increasing on this left piece until I get here, and it needs to be concave down as it's increasing. And that's natural. If you're going to make this a max, it kind of has to be concave down. Now when I pass this max, it switches to decreasing, but the concavity stays down. Okay, so coming up here, concave down, reach the peak, stays concave down until we get to our inflection point. There it's going to switch to concave up, but it stays decreasing. Okay, so increasing, it stays decreasing all the way to to the last red dot. But when it passes through this one, that's when the concavity changes. So let's start trying to do that. Okay, so I come in, increasing, concave down. Reach my peak here, switch to decreasing, but it stays concave down, right? It's still like an upside down bowl and then we need to pass through this other point we plotted. And the significance of that point again, it changes to concave up. Notice it's still decreasing, but now it's like an upright bowl. Continue in that trend, concave up, decreasing, until we get to our min. At this minimum, notice on our notes down here, it switches from decreasing to increasing, but the concavity stays upward. Okay, so continuing on, we switch from decreasing to increasing. It's still concave up, like an upright bowl. And then it just stays in that trend forever. So this is our guess for the graph of f of x. It's not 100% correct, it's an approximation, but it's got the important features. One thing, probably the biggest thing we're missing, are the x-intercepts. I didn't really know where it crossed here, and that looks like it's the only x-intercept, right? Because this one, since it's up above here when it hits its minimum and it goes up. So you could try to find the x-intercept. Now that's not going to be the easiest problem, right? We all know from pre-calculus how you find x-intercepts. You plug in 0 for y and solve for x, but that's not the easiest equation to solve for x because of being cubic. So you could do it, and you could use a calculator to help you, but kind of the point here is, can you do this without a calculator or a computer? So anyway, this may or may not be in the right place, but for these types of problems, we're really just trying to get some of the important features that we've discussed here and just get a pretty good approximation for what the graph looks like. This is another curve sketching problem. And looking at this formula, we see something we need to discuss that we didn't see in the last example, and that is because it's a fraction, it's undefined at any value that makes the denominator 0. So this function g does not exist at x value 2, since that would make the denominator 0. So we'll need to keep this in mind when we graph this function. It shouldn't have a point with x-coordinate 2. It also will affect our analysis of the increasing, decreasing, or actually it's the part about local max and min, so we'll come back to that when we get there. But from pre-calculus, we also know this tells us we have a vertical asymptote at the line x equals 2. So we'll need to make sure to put that in our final graph. Okay, so let's start with our increasing, decreasing analysis. So we know we need the derivative, g prime, and we'll need to use the quotient rule. So our new denominator will be the original denominator squared. And then we take bottom times derivative of the top, which is 2x, minus top times derivative of the bottom, which is just 1. Now let's simplify. I'm going to keep the denominator as it is. And in the numerator, I can distribute across parentheses. So I'm going to get 2x squared minus 4x. And then distributing the minus sign, we get minus x squared plus 3. So then we can combine like terms in the numerator. So 2x squared combines with minus x squared to become plus 1x squared. And then we've got a minus 4x plus 3. Now remember, we like to factor the derivative if possible, and notice the numerator here factors to x minus 3 times x minus 1. And then the denominator is still the same. Okay, so that's good for g prime. Now we use that to find our critical numbers. Okay, so the first thing we do is find values that make g prime equal to 0. So if you take the factored form of g prime and set it equal to 0, because it's a fraction, the only way a fraction can equal 0 is if the numerator equals 0. So all we really need to do is set the numerator equal to 0. And then now notice this is a product equal to 0, so we set each individual factor to 0. And then solving those, we get 3 and 1. Those are two of our critical numbers. Now let's check the second way we get critical numbers, values that make g prime undefined. So notice here, because we have a fraction, it would be undefined if the denominator is 0. So at x equals 2, this is another critical point. Okay, so the next step, we're going to create our number line, and we have 3 critical numbers to put on our number line. So we'll do that on the next slide. So I've summarized at the top some of the things we found already. We just found there were 3 critical numbers, 1, 3, and 2, so we'll put them in order on our number line. And then we'll choose a test point. This time we have 4 subintervals. So I'm going to choose 0, 1.5, 2.5, and 4. And then we're plugging into g prime. And we always want to use the factored form if you can get it factored. So here's what that looks like. Notice the denominator is squared, so that one's easy. That factor will always be positive. So when we plug in 0, in the numerator we're going to have -1 times -3, and then the denominator is always positive. So that overall result will be a positive number. When we plug in 1.5, the first factor will be positive, but then 1.5 minus 3 is negative. Denominator is always positive, so those 3 combine to make a negative number. When we plug in 2.5, so in the numerator, we'll have plus and minus. Denominator is always plus. Those 3 make a negative. And then finally, when we plug in 4, everything is going to be positive. So of course the overall result will be positive. Okay, so this tells us about increasing, decreasing, right? So we'll have, where we have a plus, it's increasing. Where we have a minus, it's decreasing. Right, so let's summarize our results. G is increasing on 2 intervals, to the left of 1, and then everything to the right of 3. And then G is decreasing between 1 and 3. Now technically we might want to list these separately, because remember, maybe we should make a note here, G is undefined at 2. So if we tried to lump those intervals together, the problem is it includes a point where it's undefined. So I'm going to keep them as 2 separate intervals. It's decreasing from 1 to 2, and then it's decreasing again from 2 to 3. Okay, now we can use these results to find our local max and min. Now here's where I said we have to be careful, because in this g of x, our function, it was discontinuous at a point. So if we had had, say, a minus to a plus, usually we say that results in a local min. If it's G's undefined there, right, it can't be a local min. Okay, so just that, this is an example of, I can kind of point out why you have to watch out for that. It turned out not to matter here anyway because it's minus on both sides. We wouldn't have made that conclusion anyway about having a local min or max at 2. So let's look at our other points. Here it switches from increasing to decreasing. Right, so we visualize this kind of curve. That tells us we've got a local max here. Okay, so we've got a local max at x value 1. Jumping over to 3, it switches from decreasing to increasing, so we've got a local min here at x equals 3. And just like in the last example, it helps to find the whole ordered pair. So let's find the y value that goes with each one of these. So here we need, it's actually g, not f, we need g of 1. So here, go back to g, don't use g prime. When we plug in 1, we're going to get negative 2 over negative 1. So that simplifies to positive 2. So the ordered pair is x value 1, y value 2 is a local max. Now we do the same thing for our local min. We plug 3 into our formula for g. So the numerator will be 9 minus 3, which is 6. Denominator 3 minus 2, which is 1. So we get 6. Okay, so our local min is x is 3, y is 6. Okay, so that finishes a big part of our analysis. The next part is concavity, so we'll do that on the next slide. Now we're ready to look at concavity, so we're going to need g double prime. So I copied our formula from g prime that we found earlier. So this is the way we first simplified it, and then we took another step and factored it. You can use either one of these for finding g double prime, but it's easier if you notice here in the numerator we have a product. So when you get to derivative of the top, you'd have to use a product rule. Whereas over here, the numerator is not a product. So it's going to be easier to use this version to find g double prime. So we're dealing with a quotient, so we need to use the quotient rule. In our new denominator, we're going to take the original denominator and square it. So right now the denominator is x minus 2 squared. When we square it again, it becomes to the 4th power. Now in the numerator, we take bottom times derivative of the top. So that's just 2x minus 4 for the derivative of the numerator. Minus top times derivative of the bottom. Now that's going to be a chain rule problem, right, because we have this inside part that's being squared. So the outer function is the squaring function. So using the power rule, you bring the 2 down in front, reduce the power by 1. So that gives us 2 times x minus 2 raised to the 1st power. Now multiply by the derivative of the inside part. The derivative of x minus 2 is just 1. Now we need to do some simplification. We'll keep our denominator the same. Okay, now let's think about how we want to do this. So one option is to square this out and then distribute this parentheses over that one, and then distribute all of this, but that's a huge amount of work. If you look for some other options, notice that x minus 2 appears in both terms. And then here, that's actually, if you factor out 2, that's another factor of x minus 2. So I think I'll start by factoring out x minus 2 from both terms in the numerator. Okay, so now from this term, we've pulled out one of these factors, so there's still another x minus 2 here, and then that's multiplied by 2x minus 4. But I'm going to write that 2x minus 4 by, like I said, if I factor out a 2 from that, that leaves another x minus 2. Then minus, now we're on to this term. We just factored out x minus 2. And I'm going to leave this 2 out. I'm not going to distribute it. So I have 2 times what's in the parentheses here. Now let's look at what we can do. So notice this x minus 2 can cancel with one of these x minus 2's. So let's do that. In our next simplification, the denominator, we lose one of these factors, so now it's cubed. And then we've canceled this out, so that's gone. Now here, I can write this as x minus 2 quantity squared, but I could also, since 2 appears in both of these, I could pull the 2 out in front. Okay, so now in the brackets, I've got, and instead of writing it x minus 2 quantity squared, it might help if I actually multiplied that out, because then I could combine like terms with what I have over here. So sometimes you have to play around until you get the best simplification that will make this easiest to work with for finding our next analysis. So the 2's gone, I factored it out. I'm going to FOIL that out. So I get x squared minus 4x plus 4. Now on the next term, I've already factored out the 2. I'm just going to distribute the negative sign. So minus x squared plus 4x minus 3. Now I'm going to look at combining like terms. Notice I have x squared minus x squared. Those cancel. Then I've got minus 4x plus 4x. Those cancel. So all that's left in the brackets is 4 minus 3, which is 1, right here, those two. And then there's a 2 out in front, so the numerator is simplified really nicely to just the number 2. And the denominator is x minus 2 cubed. That's a nice simplified version of g double prime. So that took our whole slide just to do that calculation. So we'll go to a new slide and we'll start our concavity analysis using that formula for g double prime. So now we have our second derivative from the last slide, and then we're going to use this test point method to determine concavity. So remember before what we did was we took g double prime and set it equal to 0 and solve for x. So when we do that, here's the formula for g double prime. We set it equal to 0. But this fraction could only, any fraction can only equal 0 if the numerator is 0. And here the numerator is always 2. So this has no solution. And I didn't mention this before, but you should also look for points where g prime, double prime, doesn't exist. Just exactly the same as critical numbers, right? For critical numbers, you use the first derivative, and you look at these same two things, where the first derivative is 0 and where the first derivative is undefined. Now we're doing the same things for the second derivative. And this g double prime, notice the denominator would be 0 if x is 2. So this is a number we need to put on our number line. That's the only one that we need to put on it. So that creates 2 subintervals for choosing test points. So I'm going to choose 0 and 3. And then for this test, we plug into g double prime. Notice this is not what we call the second derivative test. We actually haven't been using that test in the past couple of examples. Remember, that test is an alternate method for finding local max and min. It's not the test for concavity. This is called the concavity test. Anyway, so for G double prime, here's the formula. That's where we're going to plug in our test points. So when I plug in 0, the numerator is always 2, so the numerator is always positive. Denominator will be negative 2 cubed, which is still negative. So overall, we're going to get a negative number there. And when I plug in 3, the numerator is positive. The denominator is 1 cubed, which is positive. So we get a positive result there. So in terms of concavity, the minus means concave down, the plus means concave up. And we can summarize our results using our interval notation. So G is concave up to the right of 2. So the interval notation would be 2 to infinity. And then G is concave down to the left of 2. So that interval would be negative infinity to 2. And then along with our concavity analysis, we discuss inflection points. Now the issue here, it looks like 2 should be an inflection point, right? Because concavity changes. But 2 was our point of discontinuity. G is not even defined at 2, so you can't have a point there to even talk about an inflection point. So 2, G does not exist at x equals 2. So this can't be an inflection point. So now we've completed all the analysis, so on our next slide we'll summarize everything and piece it all together to create our graph. So I've summarized all the pieces we found, so we're going to put all that together to create our graph. So I need to mark some tick marks, so let's look at the important numbers for x first. So x equals 2. These are x intervals, so 1, 2, and 3, 1 and 3. So we want to make sure we go out a little beyond all of that. So let's say we go out to 5 in the positive direction. We don't really need to go as far in the negative direction because there are no negative x values even mentioned here. Now for y values, the only points we have that include y values are here, so 2 and 6. So let's go up a little beyond that. I know I have a vertical asymptote, so I want to go even higher just to show that. I'm going to go in units of 2. Okay, and then we'll go down just a few in the negative direction. Now let's plot our points. So there's only 2 points that we found so far. The point 1, 2 is a local max, and the point 3, 6 is a local min. That might seem strange to see a min higher than a max, but these are local, right? That can happen. Now, if you remember last time, I put number lines directly below our graph to mark some of the things we found. So increasing and decreasing. Notice the dividing points are 1, 2, and 3. Put them directly below the corresponding points on the x-axis. So I've written that it's increasing to the left of 1, and then again to the right of 3, and then the 2 intervals in between, it's decreasing. And then for concavity, we'll make a new number line because it has different points on it. The only point you see in the concavity intervals is the number 2. And so we found that to the left of 2, it's concave down, and to the right of 2, concave up. Now before we do anything else, remember there was one important thing we found here that was separate from all this calculus analysis, and that was we had a vertical asymptote at x equals 2. So I'm going to sketch that in as a dashed line. Okay. Now let's start thinking about the shape of our curve. So as we come in from the left, it's increasing and concave down. And we want to hit this point as we come in from the left. When we hit that max, notice it switches to decreasing, but it stays concave down. So you can imagine like a mountain peak here would be concave down. And then we get to this asymptote. It stays concave down, it's not going to switch, and it's going to just approach that asymptote going down. So I think we can go ahead and sketch that piece. Concave down, increasing, hit the dot, it starts decreasing and stays concave down, and then approaches this vertical asymptote going downward. Right, so if we hadn't done this analysis, we would have known there's a vertical asymptote here from pre-calculus, but we wouldn't have known if it approached it going up or down. But since we know it's decreasing as it gets closer there, it has to approach it going down. Now we didn't know exactly where the x-intercepts are. We could have tried to have found those. It actually wouldn't be hard because this it's pretty easy to do that. We may come back and discuss that later, but let's just do our current analysis now. Now it's going to jump across this vertical asymptote because a graph never crosses its vertical asymptote. And now we have this new piece. We know it passes through this point as a minimum. It comes in from the left, decreasing, and then after it passes that point, switches to increasing. And the whole time, this piece is always concave up. Okay, so that means it comes in from here, decreasing, concave up, hits the minimum, switches to increasing, but still concave up. Notice that tells us it's approaching our vertical asymptote on this side going up, and then this part goes up to infinity. So that's our best guess at the graph of g of x. Now I guess we could discuss the x-intercepts, right? If we wanted to be more precise, we could find those. We could also find our y-intercepts, right? So for x-intercepts, you set y equal to 0 in your formula. I'm just copying the formula for g of x, and I replaced g of x is y, so I replaced it with 0. So then we've got a fraction equal to 0, and as we've discussed before, the only way that could happen is for the numerator to equal 0. And then you can solve this for x. So we get x squared equals 3, which means x is plus or minus the square root of 3, which will be 1 point something, right? So let's locate these. 1 point something is here, right? That's one of them. That's the square root of 3. And this other one, it turned out, should have been a negative number, right? Because it's supposed to be negative square root of 3. So I should correct that, make it a little bit wider. If I can get it to erase. There we go. Okay. So now here's, oh, I still didn't do that right because it should be negative 1 point something. So let me erase that again. We'll get it here, get it right here. So negative square root of 3 would be around here. Okay, so now I'm going to, before I sketch it, let's go ahead and find the y-intercept. Otherwise I'm going to have to erase again and correct that. Y-intercept is always the easy one. Just plug in 0 for x into your formula for g. So looking at the top left for that formula, when we plug in 0 for x, we'll get negative 3 over negative 2, which simplifies to positive 3 over 2, which of course is 1.5. So we can plot that here. 1.5 would be about here. Wow, that's hard. That's going to be really hard to keep it concave down and passing through all those points. Woo. Well, we tried, but sometimes this can be challenging. Okay, that should all be concave down. Okay, doesn't quite look, I sort of had to make it concave up to try to get it to fit, but you could graph this on a computer and just see how it looks there, see how we did. Hopefully this is pretty close to correct. And you can see how finding those intercepts helped us make it a little more precise. The way I had sketched it at first, I didn't make this piece quite wide enough. I really don't know how wide this should be, right? How much should I have stretched it? Or should it be steep or less steep? We don't have that kind of information. You could plot a few more points if you wanted to make that more precise, like plug in 4 for x, plot it, plug in 5 for x, plot that point. Okay, so on your tests and quizzes, I'll mainly be looking that you incorporate all of these features. I'm not going to be concerned about that level of detail with how steep you make things, right? So to summarize what we did today, we finished section 4.3, which we had started earlier, on what derivatives tell us about the shape of a graph. So my summary here actually includes some of the points we discussed last time. I just thought it would be helpful to see them all together here. So we saw how we can use the first derivative to tell us where a function is increasing and decreasing. And that in turn helps us locate the local extrema. And then starting today, we discussed concavity, and we saw how the second derivative will tell you where the graph is concave up and concave down. And then related to that are what we call inflection points, and that is just the location of points where the concavity changes. We also learned the second derivative test, and this is an alternate method for locating your local extrema using the second. You use both the first and the second derivative in that test. And then finally we put everything together to see how we can figure out the graph of a function based on all of these points. So these last few examples we did were of curve sketching, and these are sort of involved problems. There are lots of parts to it, and then piecing everything together. All of that takes practice, so make sure you do all of the homework problems, and I would suggest doing more problems until you start getting comfortable with these types of problems.